So welcome to this Meow video seminar with Robert Robere from McGill. So Robert is going to talk about composition or lifting, and this is a method or a technique that has had a profound impact in many areas of theoretical computer science, including proof complexity, with many people contributing, and Robert has been one of the main movers and shakers, and now he's going to tell us about his view of this. So thank you so much, Robert, for agreeing to give this talk, and it's over to you.
All right, thanks for having me do the talk, Jakob. Yeah, so today I'm going to talk about proof complexity, lower bounds, using composition or lifting. In particular, I mean, maybe a subtitle of this, maybe a subtitle of this could have been like a personal view. I just wanted to test that my actual iPad worked. Okay, so yeah, so this is going to be a somewhat personal view on lifting and proof complexity. So let me just kind of dive right into it. So what's the sort of summary of this talk? Well, it's that one of the most powerful tools that we currently have in proof complexity and beyond, and many other areas of complexity theory, is the tool of composition. And so what's composition? Well, this is hopefully a proof complexity audience. So let's talk about composition in this setting. So so we're always going to be thinking about unsatisfiable CNF formulas. And then I'm going to let G be some sort of gadget function. And the idea of composition is to take all the variables, of F. Sorry about that. Okay, cool. So the idea of composition is to take all the variables of F here and substitute them by the function G evaluated on some new family of inputs. So these new guys, x1, x2 up to xn, these are just completely new strings of inputs that are all going to get substituted in here. Okay. And then what does a composition theorem or a lifting theorem say? Well, ultimately what it says is that if we have two proof systems or something else, as we might see, and the proof systems could even be the same, then lifting theorems are going to relate complexity measures of P refutations of F and Q refutations of the composed formula, F composed with G. Okay. So let me kind of give a sort of meta lifting theorem, I guess you could say, sort of a broad description of what a lifting theorem looks like. So if we have some unsatisfiable CNF formula over variable Zi, and if we have two proof systems, which it might helpful to intuitively think of P as being like weak and Q as being strong, then sometimes you can find a gadget function such that after doing this composition in F with this gadget function, the best Q proof of the composed formula is basically the same as the best P proof of the uncomposed formula, maybe with some extra overhead that's needed to deal with this gadget G. So where does the strength of this come from? Well, it comes from the fact that if P is weak, and so we can actually prove lower bounds for it, and Q is strong, so which means we couldn't prove lower bounds for it, then this theorem right here would lift the lower bounds from P to new lower bounds on Q. Okay. And now there's a few caveats here. So what do I mean by it? So sometimes actually turns out to be more often than you could think. And we usually have a pretty good guess on what a good choice of gadget G would be as well. And when I say most efficient, well, I mean, if you think about proof complexity or in any other complexity theory, if you're familiar, there's lots of different standard complexity measures that we consider. And indeed, there's lifting theorems that sort of relate all of these, like many of these measures to each other. So for example, it could be the size of the proof or the depth of the proof or various definitions of width or degree of the proof. And also, crucially, when I say most efficient Q proof and most efficient P proof, the complexity measures that I measure in Q and P can even be different in some of these theorems. So the main takeaway of this slide is that these theorems are really flexible, really powerful tools that can really prove bounds on a wide variety of different complexity measures. Okay, so what's my goals for today?
Just a question, Robert, or a comment really, if you go back to the previous slide, that this composition F of G, I mean, there's some way that we have agreed on before which actually turns this composition into another CNF formula.
Yeah, we'll talk about that in a little bit. So this will ultimately be another CNF formula usually, but yeah, absolutely.
Okay. Thanks,
yeah.
Rick.
It depends on the gadget. Okay, so what are the goals for today? I have 3 goals ultimately. So first, I want to give sort of an introduction to lifting and proof complexity with some simple examples, some very, very simple examples which I think are probably even folklore, but I also think dovetail nicely into this perspective on things. So in particular, at the very beginning of the talk, we'll go over some elementary lifting examples for resolution. So second, kind of my broader goal for this talk is less to get into the very technical details of any one specific lifting theorem, and more talk about the context in which I think these theorems fit. So I think that these theorems fit very naturally inside the bigger theory of proof complexity and circuit complexity, and in particular, they're closely related to the theory of monotone feasible interpolation. So kind of my second main goal is to sort of discuss this relationship between a lot of the lifting theorems that exist and monotone feasible interpolation. In particular, oops, lost it again. In particular, I'd like to talk about some of the relationships between proof complexity, circuit complexity, and communication complexity. And in some sense, I want to discuss how lifting theorems form a type of converse to monotone feasible interpolation. And if you don't understand what that means, don't worry about it. We'll get to it later in the talk. So then for people who want to stick around for the third part, I'd like to outline for you sort of a general theory, which I believe captures most of these relationships that exist. So this is a general theory of a query and communication TFNP. So TFNP, if you're not familiar with it, is this total search problems in NP. And in particular, we'll see that this will in some sense provide a generic monotone feasible interpolation theorem. And actually, most of the lifting theorems that occur in proof complexity can be interpreted inside this theory. So I kind of think that this is the generic context. This is the best generic context in which to understand most of these results. Okay, so without further ado, let's go to part 1. So do the introduction. Okay, so what are we going to see first? Well, first I want to show you 2 simple examples of lifting theorems. The first is an example that lifts resolution width to size, and the second is going to lift depth to tree-like size. Okay, and kind of the key thing that I want everyone to keep in mind while you're watching this part is the sort of connection between refuting and total search problems. And this is a really important theme that's going to come up again later in the talk. Okay, so what's resolution? Well, likely everybody here knows what resolution is. Okay, so lines in the resolution proof system are clauses, and we have 1 or 2 deduction rules. I'm going to have 2. So the first rule is going to be the resolution rule, and this just takes 2 clauses that differ on exactly 1 literal with opposite signs and deduces their or. And then the second rule is this weakening rule, which takes in a clause and it deduces just adds any literal to it. Okay. This second rule is also only being added for convenience. We don't really super need it. There's usually ways to eliminate it. Okay, so here's an example proof in resolution. So we can see here we have some unsatisfiable formula here, and then so at the leaves here I have these input clauses. From these clauses, I deduce new clauses by resolving on some variables. So here I've resolved on x1. Clauses can be reused in particular in full generality. Once I deduce a clause, I can use it twice in order to deduce new clauses. And then ultimately we deduce the empty clause, which is a proof that the formula is unsatisfiable. Okay, so we also have some natural complexity measures like length, for example, is one, the number of clauses in the proof. A second is the width, which is a second very important measure. The width is the largest number of literals in any one of the clauses inside the proof. And finally, the depth, which is just the length of the longest path in the proof. Okay, so if we just look at this refutation here for a concrete example, well, this proof has 10 clauses in it. The depth is 4. We have a length 4 path here. And then the width is 3 coming from this input clause here. Okay, so hopefully this is just review for everybody. Okay, so now I'm going to use L sub res to mean the shortest length of any resolution proof for F, W sub res to be the shortest width, and D of res to be the shortest depth. And maybe it should be somewhat intuitive that these three measures cannot be optimized at the same time. So there's proofs that there's formulas that kind of separate all three of these measures from each other. Okay, so now let's talk more about this composition, but in a little bit more detail. Okay, so if we start with the CNF formula, and let's start with a really simple example. So I'm just going to compose with a 2-bit XOR. Okay. So well, earlier in the talk, I kind of defined for you this very simple, like the definition of the XOR function. But if we start with F being an unsatisfiable CNF formula, then we have a little bit of a weird thing, right? Because F is going to be semantically equivalent to 0. So if I compose F with an XOR, the results will still be semantically equivalent to 0, right? So this is what Jakob was alluding to before about how we need to come up with some syntactic way of, after doing this composition, rewriting it into a new CNF formula. So for the case of XOR, and this won't always be the case, I'm going to do the following composition. What I'm going to do is I'm going to basically, every time I have a ZI variable, I'm going to substitute it for the CNF encoding of the XOR of XI and not XI, of XI and YI, sorry. And whenever I have the negation of ZI occurring in some clause, then I'm going to substitute it with the CNF encoding of the negation of the XOR. Okay. And then once we do that, well, then we can just rewrite this into a new CNF formula just by distributing the ORs over the ANDs. Okay. So, and then we'll see an example of this on the next slide, but if you can kind of do this in your head, then you'll see that, well, if I started with a formula that had S clauses and width at most W, then this new CNF formula, well, the size is basically what's going to happen is the size is going to blow up by a 2 to the W factor from this distributive law. And then the width is going to at most double because I'm basically replacing every literal with 2 literals in the resultant clauses. So just to see an actual example of this in action, I mean, here's a really simple CNF formula, Z1 and Z2, not Z2 or Z3. So Z1, we're going to substitute it with the CNF encoding of XOR. Z2 is going to get the CNF encoding of the negation of XOR, and Z3 gets XOR as well. Then after the distribution, you can kind of verify that you'll get this set of clauses here. So Z1 gets substituted with here. This is just this substitution occurring here. And then not Z2 or Z3 gets substituted with both of these. And then when we kind of blast it all out to CNF, we get this blow up in the width and in the size. Okay. So hopefully not too complicated. Okay, so the first lifting theorem that we're going to see is going to relate resolution width to resolution size. All right, and now width to size is kind of a famous topic in resolution. It's kind of well known that resolution width and resolution size are sort of very closely related to each other. And perhaps the most well-known example of this is this theorem due to Bensasson and Vigdersen. And here's their theorem. So what Bensasson and Vigdersen show is that if you start with any unsatisfiable CNF formula on n variables, then the size of the shortest resolution proof of F is exponential in this quantity here, which you can think of as being like 2 to the width of that's required to refuting F in some sense. Of course, it's not actually the same. What we actually need here is a gap between the width in resolution to refute it and the width of the initial formula. And if you look at the parameters here, you can see, well, as long as this gap is bigger than n, is bigger than square root of n, that is, then we'll get some sort of interesting lower bound. We won't, this lower bound won't trivialize. So the main lesson to take away from Benson-Wigderson's theorem, I think, is the following. It's just that if f is a constant with C and f, and it takes, however, whenever you need to refute f, it somehow blows the width up to something asymptotically bigger than square root of n, then you can use this theorem to get strong size lower bounds. Okay. So it's really hard to overemphasize the effect that this theorem has had on proof complexity and on the complexity of resolution in particular. It's like a really, really, really important paper. It's a really, really foundational paper. This relationship is used, this relationship and versions of it are used all the time in standard resolution lower bounds. So this is really quite an important result that probably many people here are already familiar with. But something that's kind of interesting is that you can actually get a similar theorem by a pretty much trivial proof. Okay, so what's the similar theorem? Well, I'm going to write down basically the same thing, but instead of having f on both sides, I'm going to compose f with the XOR. Okay, so if we compare it to the theorem that we saw a second ago, the main difference here is that on the length side of the equation here, instead of having the length of f, I now have the length of the composed function. And you can see this is just 2 to the exponent 2 to the width required to refute f. So now we no longer need this gap anymore in the width of refuting f, and we no longer need it to be sufficiently large. This lower bound theorem works regardless of what f we'll see. Okay, and it might be helpful to think back to the first slide, this sort of executive summary. What we're doing here is we're relating complexity measures of one type of refutation of f and the refutations of f composed with g. Well, possibly p equals q, and that's exactly what's happening here, right? If the theorem here relates resolution length of the composed thing with resolution width of the uncomposed thing. Okay, and it's kind of helpful to know. I mean, this is incomparable to this Benson-Wigderson size width relation. There's some things that you can prove with it that you couldn't prove with the other thing, and vice versa. Also, if we can refute f in length s and width w, then just by basically locally simulating the XOR in every single step, we can actually refute the composed function in length roughly s times 2 to the w and width 2 to the w. So what this should tell you is that, in fact, this naive simulation is essentially the best one, right? By locally doing this substitution and by locally deriving all of these XORs, basically you can get an order 2 to the w bound here. And in fact, like what this theorem is kind of telling you is that, well, more or less up to this factor of s, this is kind of the best you can hope for. Okay. And this is, again, sort of a theme that occurs over and over again in these lifting theorems. Okay, and then also probably people know that if I can refute something in width f, well, then I can also always refute it in size, like n to the w of f. This is just easy because there's only at most n to the w clauses of width w. And therefore, this theorem is actually pretty much tight up to a log n factor in the exponent. Okay. Okay, so I said we can get this theorem by an essentially trivial proof. So let's actually see it. So here's the theorem. So let's start with any resolution refutation of this composed function. And what I'm going to do is I'm going to hit this proof with a random restriction. Okay. And the random restriction is going to be generated by the following very simple process. For every input variable I, I'm going to flip a coin. If the coin comes up heads, then I'll set xi, one side of the input, to be a random bit. And if it's tails, I'll set the other side to be a random bit. And then I'll leave everything else to be stars, to be unset. Okay. Well, if you do this, well, it's not hard to convince yourself that if you take any clause in the proof with width bigger than t, then the probability that this clause is going to be not satisfied by this experiment is something like 3/4 to the t, right? Because every single variable is going to be every single variable in the clause will be set to the right value with probability 1/4. Right? And so this means just by taking a union bound over the proof, the probability that there is a clause in the proof that's big, that has width larger than t and is not satisfied, is going to be like the size of the proof times 3/4 to the t, which if we set t correctly, we can force to be less than 1. So if we set t to be something like log of the size of the proof, then by the probabilistic method, we can find some restriction rho that's going to kill all of the wide clauses. And in the resulting proof, every clause that's left will have width at most log the size of the original proof. Okay. And now finally, well, we have this restriction. Well, what happens when I take this very structured restriction that I chose here and I plug it back into f composed with XOR? Well, I mean, it's not hard to see that actually what you get is essentially just a copy of f, except with some of the variables negated, right? If I take an XOR and I plug in a random bit to one of the variables, what I'm going to get is either the other bit or the negation of the other bit, right? So the result after hitting it with this restriction is going to be f prime, and f prime is just going to be a copy of f with some negated variables. But resolution is kind of blind to all of the variables of f being negated consistently, right? It doesn't really care. So the width of these the width of refuting these two formulas is the same. And there you go. That's the whole proof. So what did we do? All we did is we hit it with a random restriction, sort of a standard technique in resolution, killed all the wide clauses, and then we're left with a low width refutation of essentially f, not f, but something that's equivalent to f with up to resolution width. Okay.
And Robert, also just for any listeners outside of proof complexity, because I see on the participant list that I think we have some that we're also using here the completely standard fact that if you have a valid resolution refutation and you hit it with a partial assignment like this, and when you simplify and then the dust settles, you still have a valid resolution refutation. So you're like recovering a resolution refutation modulo this relabeling of variables of the original formula, right?
Yeah, exactly. Thank you. Yeah, that's an important point. I did subtly use the fact here that after we hit it with restriction, if I take a resolution proof and I restrict it, I get another resolution proof. It doesn't somehow break the proof. Okay, so what happened here? Well, using random restrictions to kill wide clauses is a totally bog standard technique in proof complexity. And the key observation here is that composing f with an XOR made it more resistant to these random restrictions, right? The key place where this XOR came in that helped the enabling of the lifting theorem is that f, when I compose it with XOR and hit it with a restriction, it's now much more resistant to random restrictions. But the proof itself is still weak to them, right? A resolution proof is still weak to random restrictions. If I hit it with a random restriction, all the wide clauses are going to die. So what we're doing is we're kind of arbitraging this weakness here. And now I'll also take this time to point out that just composing with XOR in this way has been used to prove many trade-offs in proof complexity, many notably involving space and many also notably involving Jakob. And similar techniques have also been used in lots of other different proof complexity lower bounds. So one example would be like this relativization technique, which is also a kind of padding. Like it's kind of like taking the original clauses of the formula and adding in some new variables to sort of make them more resistant to random restrictions or more resistant to weak random restrictions in some sense. Okay, cool. So this is our first example of lifting. Let's see the second example. So we can also show that if we take XOR and we compose it with F, well, we just saw that we can lift width to DAG-like resolution size. Well, now let's see an example of lifting depth to tree-like size. Okay, so in fact, we get basically the exact same theorem that we just saw. So if F is an unsatisfiable CNF formula, then the size of the shortest tree-like resolution proof, this is just a resolution proof where we're never allowed to reuse any clause. It has to be in the shape of a tree. The length of the resolution proof of F composed with XOR is exactly 2 to the depth required to refute the formula. And now it's not hard to convince yourself just by this same local replacement argument, just by locally simulating the proof, that the depth to refute this composed formula is at most 2 to the depth, and therefore the size to refute anything in tree-like is at most 2 to the depth, because every node in the proof has exactly 2 children. So what this means is that this theorem actually is actually tight, right? So we can actually show that a sort of tight relationship between f and x, or up to, again, to the constant of the exponent. So just a brief reminder of what a tree-like resolution proof looks like. Well, a tree-like resolution proof is just a resolution proof that's a tree. We never allow you to reuse any clause. So I've drawn an example here. And I'm going to use this opportunity to sort of introduce a really important relationship that's going to come up again later, which is this relationship between refuting formulas and solving search problems. Okay, so if f is an unsatisfiable CNF formula, then we can associate with f this following total search problem, what I'll call a total search problem. Okay, and this is a sort of reoccurring theme that we'll see over and over again. And the idea of the search problem is the following: if you give me an assignment to the variables of f, well, then output any index of a clause that's falsified by the assignment. So this is a search problem because we're given an input and we want to find some output associated with it. And it's total because the formula is unsatisfiable. On every single input assignment, some clause will be falsified, right? And it's kind of a well-known or sort of a folklore fact in proof complexity that if I start with a tree-like resolution refutation of f, then actually tree-like resolution is essentially equivalent to decision trees that solve this search problem. Okay, so I've drawn over here an example of what I mean by a decision tree. So a decision tree now is just going to be, you probably everybody is familiar with what a decision tree is, but the basic idea is that we're going to query input bits of this formula, and then each path in this tree is going to correspond to a partial assignment to these input variables, and then we'll just label the leaves with the outputs of the search problem. So if the partial assignment corresponds to a false clause, then we'll just label the leaf with any false clause that's any clause that's falsified by the path to that leaf. Okay. And the equivalence between tree-like resolution and decision trees is sort of pretty well known, but the basic idea is that a decision tree is a tree-like resolution proof where you just flip all the arrows. So here I've drawn, like, whenever the tree-like resolution proof queries a variable in the decision tree, whenever the tree-like resolution proof resolves on a variable, the decision tree will just query the corresponding variable over here and then branch and then so on. Okay, cool. So with that, let's use this to prove the lifting theorem for f composed with XOR. All right. And this theorem is the proof of this is gonna look incredibly similar. In fact, it's basically the same as the one that we just saw. So let's consider any decision tree that solves the search problem. Okay. And we'll let rho be a partial assignment that's generated by the exact same experiment. So just for every single index, flip a coin and set the xi variable to true to a random bit if it's heads and the yi bit to a random variable if it's tails. Then, well, what happens to the decision tree after we do this? Well, it's not hard to see when you think about it that if I have a path of length t in the decision tree, it's going to become pruned under this random restriction with probability 3/4, right? Because if I pick any path, I basically have t tests of variables, and I'm going to pick the opposite value of one of those variables with probability 1/4. And I get t independent chances in order to do this, right? So any path in the tree is going to get pruned with probability 3/4. And therefore, once again, by a union bound, there's going to be some path that survives with probability no more than the size of the tree, the number of paths times 3/4 to the t. And then we just do the exact same argument that we just do the exact same argument. Once again, we set t to be roughly log of the size of the tree. We get a new bounded depth decision tree that solves the restriction of the search problem. And we just saw that under this restriction, you get basically just a copy of f with some of the variables negated. So there you go. So once again, the whole formula is now robust to restrictions, yet the proof is still weak to restrictions. And so therefore we can arbitrage this difference, and then we can prove this, and then we can prove a relationship between these two complexity measures again. Okay, cool. So now we've seen two of these simple sort of lifting theorems. They relate complexity measures of the composed formulas with simpler complexity measures of the uncomposed formulas. Okay. And now what's kind of the lesson here? Well, I mean, how do these proofs work? Well, the main lesson of them is that you go from a short proof of f composed with XOR to some bounded complexity proof of the uncomposed formula. And this is often called like a simulation argument. And that's essentially what's happening here. We start with a short proof and we extract from it a bounded complexity proof in a different sense. So this intuition appears in many, if not most, of the proofs of lifting theorems in practice. And the second major lesson to take away here is that composing with a gadget, it makes your formula more robust. So it can be used to sort of arbitrage weaknesses in the proof systems. If we have a proof system and I know the proof system is somehow susceptible to some technique, then if I pre-compose with a gadget that makes your formula resistant to that technique, then usually this is a very powerful idea that can be used to generate new and interesting bounds. And taking this, you can actually generate many different lifting theorems in practice. So here's just a sampling of some of the theorems you can prove. So, I mean, we can relate, as we just saw, we can relate resolution depth to tree-like resolution size after composing, say, with XOR. We can do resolution width with resolution size, which we also just saw. But I mean, there's lifting theorems that relate many different proof systems to many different complexity measures of proof systems. So we can also relate resolution depth to the depth of cutting planes refutations, resolution width to cutting plane size if we compose with a particular index gadget, if we compose with a particular gadget, and resolution depth with tree-like cutting plane size. So there's quite a rich family of results that you can prove here using these techniques. And this is not just an isolated phenomenon that exists only for resolution. Somehow composing with this gadget, like composing really is a powerful idea that can be used to leverage lower bounds in lots of different proof systems. Okay, so that's the end of the sort of introduction, the gentle introduction to lifting. So now's a good time to sort of pause and maybe answer any questions that might be out there. If not, I'm happy to just kind of keep going. Okay, cool. Okay, so now let's move on to sort of the next topic, which is like the relationship between these lifting theorems and between proofs and other areas of complexity, in particular communication complexity and circuit complexity. So if you've seen these kind of theorems before, or if you're somewhat vaguely familiar with the literature, you probably know that many of these lifting theorems actually link together proof complexity with lower bounds in circuit complexity, in particular monotone circuit complexity. So in the second part, I'd like to sort of discuss this aspect of it, which I think is a really, really important aspect. So let's just see a sample of what one of these theorems can look like. So if I let m of f denote the size of the smallest Boolean formula computing f, you'll see a definition in a second if you're not familiar with it. And I let g be some gadget function. So if g is some function, then I'm going to let like the size of g here denote the minimum size of one of the two inputs. So g is going to be now sort of a gadget with a bipartite input domain, and I'm going to measure the size by the minimum size of one of the two input sides. Then sort of the prototypical example of a lifting theorem that links proof complexity with circuit complexity is the following. So if we start with an unsatisfiable CNF formula, then there's some function G, some nice gadget, which is the index gadget, and a monotone Boolean function F, which depends on both the formula and the gadget, such that the formula size of computing this F, should be a FG here. The formula size of computing this F is basically characterized by the resolution depth of refuting the underlying CNF formula. Okay, and we also pick up a log of the size of the gadget factor here. So this only helps us. Okay, so the main lesson of this kind of theorem is that, proof complexity lower bounds can actually be used to prove lower bounds in circuit complexity, right? And it's natural to ask, what's going on? Okay, so let's take a step back first and let's get a reminder of Boolean circuit complexity, okay? So Boolean circuits are devices that are used to compute Boolean functions. And typically they're constructed out of and OR gates from Boolean input literals. This is not always the case. You could have more exotic families of gates. In this talk, let's just think about gates composed out of and ORs and with negations at the inputs. So these are technically called De Morgan circuits, but they're polynomially equivalent to standard Boolean circuits, so no big deal. And if you're familiar with complexity theory, you probably know that one of the major open problems is to prove superlinear lower bounds on non-monotone circuit size for any function in NP. And the current record is somewhat shabby. The best thing that we can say right now is, roughly a lower bound of roughly 5n for some function which is actually computable inside P. Not even, So we can't even hope to get super polynomial lower bounds, but maybe you could hope for superlinear lower bounds. So because of this, it's kind of common in complexity theory to look at restricted models. And one model which is particularly important for proof complexity is the model of monotone Boolean circuits. So a Boolean function is I'm going to call it monotone if whenever x is less than or equal to y, where these are two strings, think of them as inputs to f. When this is a bitwise, when x is bitwise less than y, then f of x is going to be less than f of y. Okay, and I'll say that a Boolean circuit is monotone if it has no negations. Only and OR gates. So here's an example of a monotone circuit. It's just the circuit from the slide ago, but where I've taken the negations off the input leaves here. So it's easy to see that monotone circuits compute monotone functions. Well, why? That's because and OR are monotone. And there's been significant progress on proving lower bounds for monotone circuits. Here's just two classics. We know that solving the NP complete K-clique problem requires monotone circuit size roughly n to the k. And we know the ST connectivity problem requires quasi-polynomial size monotone formula. So monotone formula size roughly n to the log n. Okay. So now that we have definitions, let me kind of outline what the goal of this second part is. I'd like to explain the connection between proofs and monotone circuits, in particular introducing some necessary background from communication complexity. And once again, this key that I'm going to lock onto here is this solving total search problem. So this unsatisfiable CNF search problem we saw from the first part is going to really play an important role here. And then I want to relate lifting to the theory of monotone feasible interpolation. Okay. And now, if you're not familiar with this theory, it's okay. I'm gonna introduce it in sort of a different kind of way than it's usually seen, I think. But the one sentence selling point of feasible interpolation is to show how proof upper bounds imply circuit upper bounds, and therefore circuit lower bounds imply proof lower bounds. And what we'll see is that lifting will give a partial converse, in quotes, to interpolation. It won't actually give a converse, but in some sense, it will show how to give proof lower bounds will imply circuit lower bounds. And there's actually quite a lot of interesting things you can say here. And then finally, we'll give a little brief survey of lifting results between proofs and circuits. Okay, so in order to sort of properly introduce this stuff, we need to talk about communication complexity. So communication complexity in this setting is going to play a role similar to decision trees played to proofs in the first part of the talk. So if I let S be some relation with a bipartite, I'm going to think of this as kind of I'm going to think of this as kind of a search problem where we get X, Y as input, and then we have to find an O that's consistent with S. Okay, then I'll say that this search problem is total if for every single input in the domain, there's some output that's consistent with it. So there's some O that we can actually find a solution to it. Okay. And I'll say that S is and of course we can say S is a search problem. You know, we're given X, Y, we want to find an O such that X, Y, and O are all in the relation. And we're going to be studying this sort of in the model of two-party communication. Okay. So we have two inputs. The idea of communication complexity, here's a quick review. We have two players, Alice and Bob. Alice is going to get one input X. Bob will get the other side of the input Y. And then they'll sort of communicate over this channel. They're only allowed to send bits to each other over this channel. And then they want to, after communicating information about their inputs, they'll together learn an output of the search problem that's consistent. Okay. And then the complexity is going to be the minimum number of bits that need to be communicated over this channel in order to determine what the output is for every single input. And I'll let FP of S be the minimum number of bits that must be communicated in any one of these protocols. Okay. But this is actually not how I kind of want to think of it. It'll be more useful. This is sort of the standard definition. I think it'll be more useful for us to think about communication protocols in a different way. And this is in the language of what I'll call a rectangle tree. Okay. So here's a picture of a total search problem. Okay. So it's going to look like this. Here's the bipartite input domain, right? Like X cross Y, drawn in this way, with sort of X's on the rows and Y's on the columns. And now all of these blocks correspond to different answers to this search problem here. Okay. So now Alice and Bob, they're given some input, so X and Y here, and they want to figure out the name of some output that's consistent with their input. So in this case, it would be either O sub 2 or O sub 4, right? And they can do this by communicating bits back and forth to each other, right? So what are they going to do? Well, maybe Alice is first going to start by communicating a bit, and she's going to say, okay, well, my X is in the top half of this rectangle up here. And then based on this answer, Alice and Bob can kind of descend to knowing that, well, her input is somewhere in the top half of this tree right here, right? And of course, if her input was in the other half, if she communicated a 1 instead, that would tell them they were on the other side. So then now maybe Bob communicates a bit back and says, okay, well, I'm on this half of this rectangle here, right? So, and then from that, they can again descend to a side here. And then, after they proceed for many, many steps, I haven't, drawn out the entire tree here, but after they proceed down for many, many steps, they eventually isolate themselves to this rectangle right here. And inside of this rectangle, they both know that the only answer is O4. So they can stop and then output it. And then, so what I'll call, so each of the objects that are reached at this step of at each step of the protocol is called a combinatorial rectangle. It's just a subset of the input domain that's also kind of, that can be written in a bipartite way. And the lesson of this slide is that each protocol gives you a tree of rectangles. Okay. So what do I mean by a rectangle tree? Well, here's the 3 properties that will define a rectangle tree. So the root of the tree is going to be everything, X cross Y. So this just means that every possible answer is sort of feasible at this root node. Each of the leaves are what we'll call monochrome. So like every single leaf has some unique solution associated with it, and that's the solution that's output at that leaf. And then if I have some internal rectangle, then if this rectangle has children R1 and R2, then R is contained in the union of the two children. Okay, so here we're typically in a communication protocol, it actually splits exactly, like it just, after querying a bit, we split exactly into the partition of the two children. But you can actually prove that if you just have this weaker condition, then the size of the tree is not going to change by very much. Okay. And now, so the size of the tree, I'm going to be measuring by the number of leaves, which is, just basically proportional to the size of the whole tree. And this should hopefully somewhat remind you of this simulation of tree resolution by decision trees. At very least, this object is somewhat similar to a decision tree, right? At every single node, we're kind of doing some sort of query and then branching based on the results of this query. Okay. Now, what's sort of so this is an example of a communication protocol with a total search problem. What's a canonical example of a total search problem in communication complexity? We saw in proof complexity, the sort of a canonical example is this unsatisfied clause search problem. Well, in communication complexity, we have an analogous search problem, which is something called a Karshmer-Wigderson game. Okay. And here we're going to focus on monotone Karshmer-Wigderson games, but a non-monotone theory exists as well. So if I let f be some partial monotone Boolean function, so just think of the star as being kind of like, I don't care what the answer is, then I'll denote by mkw of f, the monotone Karshmer-Wigderson game of f, to be the following total search problem, which is just Alice gets a 1 of the function, Bob is going to get a 0 of the function, and their goal is to find an input bit I such that xi is 1 and yi is 0. Okay. And since the function is monotone, we always know that if, we know that x is less than y implies f of x is less than f of y. And this actually means that there will always exist some coordinate I where x is 1 and y is 0. Because if this was not true, then we would have that y is bigger than x, but then f of x is 1 and f of y is 0, right? So this is just a sort of a clear contradiction. So this is a total search problem. It's kind of the important point that I wanted to make. And what's kind of also nice about it is that if I look at any one of the input bits, any one of the xi's, they give me a combinatorial rectangle in the domain. And so in fact, each of these relations kind of gives you a rectangle cover, like a total covering of the input domain by these rectangles here. Okay, cool. And now, why do I say these are kind of the canonical examples of search problems? Well, it's because if you ever have any rectangle cover, this is actually just a Karshmer-Wigderson game in disguise. Okay, so if I start with any rectangle cover whatsoever of any set U cross V, then this rectangle cover is actually just the monotone Karshmer-Wigderson game up to renaming some of the input rectangles. Okay, so let's see. This is quite an easy proof, so let's just see it. So here's a picture of like an arbitrary rectangle cover, okay, U cross V. So now we have some rectangles, that are just covering this set. And now let's just pick any element in U and any element in V here. Well, for every U, I'm going to let X super U be the following string. It's just going to write down the list of rectangles that U is contained in. Okay, so this one right here, well, U appears in the rectangle R1 and R2. So we'll put down 1, 1, 0, 0. And then similarly for V, I'm going to write down the list of rectangles that V is not contained in. So it's 0 if and only if V is in Ri. So now up here, so we see V here. Well, V is contained, v is not contained in R2. It's the only one that v completely avoids. So we write down the string 0, 1, 0, 0. And now we can see, well, I mean, what's special about these strings is that they satisfy exactly the condition of the Karshmer-Wigderson game that we saw on the previous slide, right? Like if the place where these two intersect is the place where the x string is 1 and where the y string is 0. So then you can just define a function this way. So for all of the u's, just define f so that it's 1 on all of these x sub u's, and define it to be 0 on all of these y super v's. Okay, and this will actually define a function, and the reason is because this problem right here is actually total. Like this is just this is the Karshmer-Wigderson game of this function. So since Karshmer-Wigderson games and functions are kind of equivalent to one another, then this will actually give you a Boolean function. So I think that this is kind of a really important fact that is maybe, if you're not familiar with the area, if you're familiar with the area, is somewhat underappreciated. It's what this fact is saying is that somehow Karshmer-Wigderson games are like, monotone Karshmer-Wigderson games in particular, are like complete for solving total search problems, right? Like, and this explains why we're so good at proving monotone circuit lower bounds, right? If you wanted to prove lower bounds for any total search problem in communication complexity, what this result is telling you is that that lower bound is probably already giving you some kind of monotone circuit lower bound, some sort of lower bound for a monotone Karshmer-Wigderson relation, right? So proving any lower bounds is the same as proving some kind of monotone lower bound, right? And so what we can do is, if I start with any total search problem now, what you can do is you can take any rectangle cover of that. So by that, I just mean any set of rectangles which cover the whole input domain and for which every rectangle is consistent with some unique solution. And then I can consider the search problem, which is to find an element of that rectangle cover, right? And then we just saw that this will be the same as the monotone Karshmer-Wigderson game for some function. And therefore, like, this is basically the same as proving monotone circuit bounds. So there's another kind of name for problems that have small rectangle covers. And these are problems which are in NP, in communication complexity. Or in this case, because we're dealing with search problems, this is TFNP in communication complexity. This is going to be something we'll see in sort of the second half of the talk and a bit more carefully. Okay. So maybe I'll talk about this, and then we can sort of get ready for the break. So I'd like to just spend a second talking about the relationship between Karshmer-Wigderson games and monotone circuits. The basic idea is that if I start with a partial monotone Boolean function and I have some monotone formula, then actually the rectangle tree size of computing this Karshmer-Wigderson game is just the same as the size of the smallest formula that's computing f. And the proof is also pretty simple. It's going to look a lot like the tree-like resolution to decision tree picture we saw a second ago. If I start with a monotone formula that computes my function, for example, then what I can do is for every single gate in the formula, I can associate the following rectangle. At the gate, I'm going to associate the rectangle which is 1 on the 1 inputs of f, and it's 0 on the 0 inputs of f, right? So this is like the rectangle of inputs which the gate correctly characterizes. So, I mean, you can imagine it kind of looking like this in this example. So every single formula right here gets a gate. And now all of these leaves, well, they're just going to be consistent with some input variable right here, right? Excuse me. And so when we erase the gates from the picture, what we see actually is a rectangle tree. And this rectangle tree is a rectangle tree for the monotone Karshmer-Wigderson game. And so by the earlier result, this is just going to be the same as a communication protocol. And you can also prove a converse direction as well. I mean, and what you have to think about is how to simulate kind of an arbitrary rectangle by gates. And this isn't a hard thing. It's kind of a nice exercise to figure out for yourself. Oh, sorry. I went to the same slide. Okay, cool. So just like rectangle, we can talk about rectangle trees being equivalent to monotone formulas. You can actually generalize things a little bit. This is just an aside that'll be useful for later. You can generalize things a little bit and talk about rectangle DAGs. So if you actually care about characterizing monotone circuit size instead, what you can do is you can write down a DAG of rectangles for the Karshmer-Vigdorsen game, and it turns out that the size of the smallest DAG is going to characterize the smallest circuit size. And a rectangle DAG is exactly the generalization of rectangle trees that you would expect. Instead of having a tree now, you have a directed acyclic graph of rectangles, but all of these like internal properties are still satisfied. So the root node of the graph is going to be X, is going to be everything. It's going to be all the possible inputs. The leaves are again going to be monochrome, and then if I have any internal node, then it'll be covered by the two child nodes. And now, so let me just kind of summarize this sort of brief excursion into circuit complexity, and then in the second half we'll start linking together the proofs to the circuits. So the theory of total search problems and communication complexity is closely related to circuit complexity, and in fact, it's kind of like in some sense equivalent to circuit complexity, right? At least for these two models that we've just seen a second ago, the rectangle trees and rectangle DAGs. And we only saw the monotone theory, which is in some sense complete for total search problems, which is why I focused on it. But Karshmer and Vigdorsen showed that also you can develop a nice non-monotone theory as well. And then the main kind of lesson I'd like you to remember is that if you start with any total search problem in TFNP, that is a search problem which can be defined by a small rectangle cover, then this is actually just equivalent to the monotone Karshmer-Vigdorsen game for some partial monotone function. Okay. And then we just saw that trees and DAGs correspond to monotone formulas and circuits. So what we're going to see next is we're going to take the first part of the talk, talking about proofs and search problems there, and the second part, and now we're going to try and link them together. And this is where the lifting theorems will live. Okay, so it's 9 a.m., so maybe now's a good time to take a break.
So yes, at which point we should note that you woke up slightly earlier than maybe some of us in Europe did, Robert, so thanks for that as well. I mean, we're approaching 3 p.m. In Central Europe. Before we take a break, are there any questions, comments, anything? Please speak up. So do you maybe want to give a quick teaser for, so the plan now is, I guess we'll have like a 5 to 10 minute break and then we'll be back. Mm-hmm. Do you want to give I guess you already gave kind of a teaser a little bit for the second half. Do you want to say, like, I don't know, a few seconds more about like what we should expect?
Yeah. So what we're going to see now is, so we've seen search problems for CNF formulas. And now, so what I'm going to do is I'm going to show how to take the search problem for a CNF formula, and I'm going to convert it into a search problem for a communication protocol. And using this will be the sort of the fundamental link between communication, between communication complexity and monotone circuit complexity and with proof complexity. So this lifting theorem from proofs to circuits, this is the kind of space that this is going to live in.
Thank you. So again, if there are no questions at this point, then I guess we'll just take. So what should we say? People want to grab coffee or have a bio break or something? Should we have a maybe like a start in 9 minutes from now or so, 10 past the hour?
Sure.
So thank you so much for the wonderful survey talk so far, Robert. Thanks a lot. And we'll be back in then 9 minutes from now. Thank you. So we're back after the break for the second more technical part of Robert's talk. And it's over to Robert just in a second, but note that there's in the chat, there's a question about citations. Would there be any list of references at the end or anything that you can say? Maybe about some upcoming survey on this topic? Like this would be great to have a survey on this, no? I mean.
Okay, so list of citations I can provide offline if you send me an email. I don't have them on the talk exactly, but that's easy to provide. As for a survey, stay tuned. Maybe. Okay. Okay, yeah, I guess if we're good to go, then let's do it. Okay, so we finished off. Let me just get back to where I was a second ago. I don't know why that's happening. Okay, so all right, so the next goal is to kind of link together part one and part two. And this is what we're going to show is how to get Karshmer-Wigderson games from these unsatisfiable clause search problems. Okay. All right, so how do we do this? Like what's the basic idea of doing this? Well, it's actually kind of simple. We're going to do it in kind of the dumbest possible way. If I start with an unsatisfiable CNF formula, okay, so we have this search problem associated with it, given an assignment, find a false clause. Well, now here's kind of a pictorial representation of what this could look like. So if this is all of the assignments to the input variables, then every single clause is going to falsify some block of these assignments, right? And maybe they'll overlap. But the important point is that since it's unsatisfiable, every single assignment here is going to be falsified by one of these input clauses, right? And now to turn this into a communication problem, I'm going to solve this in a very simple way. All I'm going to do is I'm going to take the input variables and I'll partition them into two sets, X and Y. So what does this do to this picture here? Well, what it does, we get a new search problem where we now have this kind of bipartite input domain, the assignments to X and the assignments to Y, and all of these rectangles, all of these false clauses just become rectangles. And you can see here that the intersection pattern of these rectangles is consistent with the intersection pattern of the clauses back over here, right? So this is now a rectangle covering, if you will, of this set, 0, 1 to the X cross 0, 1 to the Y, right? And we saw a second ago that rectangle coverings are equivalent to monotone Karshmer-Wigderson games, right? So that's going to be the main connection. So if you'd like to see the sort of formal definition, if we start with a search problem associated with an unsatisfiable CNF, then if we take any partition of the input variables X and Y, then we can consider this partitioned search problem where you just partition the inputs. We haven't done anything special. And then given X and Y, we want to find an I such that the clause where I plug in the assignment to both the X and the Y is false. And then the main observation is that since CI is a clause, this set right here of false assignments is actually a rectangle. Here we're crucially using the fact that it's a clause, right? Because it's a conjunction of variables. So any false assignment is going to be like a false assignment to the first part and a false assignment to the second part. So these clauses now yield a rectangle covering of this search problem. And therefore we can, because of what we saw a second ago, any rectangle covering should be the same as the Karshmer-Wigderson game of some function. So the question is, what is the function? Like, next question I want to talk about is what should be the monotone function that corresponds to this funky search problem? And there's kind of two answers to this. One is this monotone CSP set, and the second is called an unsatisfiability certificate. They're two different names, but essentially for the same function. So since every communication tool search problem is equivalent to a monotone Karshmer-Wigderson game, what's the function that corresponds to this guy? Well, in this particular case, there are two papers, one with myself, Noah Fleming, Tony Patassi, and Dennis Pankrotov, and one by Pavel Hrubesh and Pavel Pudlak that gave independent and essentially equivalent answers. So we use this monotone CSP sat function, which is a monotone generalization of sat. And we were kind of inspired because this function pops up all the time in these lifting theorems. So we didn't actually define this function for the first time. This function was used in many of these different lifting theorems. It just turns out that it also naturally turned out to be the right function to define this search problem right here. Hrubesch and Pudlak, on the other hand, introduced a different function called the unsatisfiability certificate that they call the unsatisfiability certificate. And I'm going to use their definition actually for this talk because I actually think it's kind of simple and nice and elegant, and it kind of deserves to be better known. So what's the unsatisfiability certificate? Well, we start with an unsatisfiable CNF, and we have some partition of the input variables. Well, once I have a partition of the input variables, I can partition all of the clauses according to these variables. So every clause now has an X part and a Y part, right? And so this unsatisfiability certificate is going to be the following function. When I'm given an input, notice the number of input variables here is the same as the number of clauses. Okay. So when you're given an assignment to this input, when you're given an assignment, well, think about the assignment as choosing a subset of the clauses somehow. Okay. And so I'm going to output 1 if I take only the X parts of the clauses where Zi is indexed, where Zi is 0. If I take this CNF formula, I'll output 1 if that's satisfiable. And then on the other hand, I'll output 0 if I look at the ones where Zi is 1, and I'll take where Ci of Y is satisfiable. And if neither of these cases occur, then I don't care. I'll just output a star. It's a partial function. Little typo, so this should be a star here. Okay, so that might be a little bit confusing. So let's just see it in kind of a picture. So if this is my CNF formula, I have a variable for every single clause here. And now if I'm given an assignment to these variables, well, I'll check 2 conditions. So first, I'll look at the zeros, and I'll look at the X parts, and I'll check if just these 2 clauses by themselves are a satisfiable CNF formula. And if it is satisfiable, I'll output 1. Otherwise, I'll look at these ones, the places where these variables are 1, and I'll look at the Y parts, and I'll ask if those are satisfiable. And if that's true, then I'll output 0. And now you might ask, well, okay, why can't this both happen at the same time? And the reason is that, well, if they were both satisfiable, then actually, in fact, the whole formula would be satisfiable. This is why I picked the zeros here and the ones here, right? Any single string now will index the whole formula, one part of the whole formula. So since the original formula was unsatisfiable, you cannot get both a 1 and a 0 at the same time. Okay. And so this, if you're familiar with this kind of these kind of things, this might look quite familiar to you as an interpolant function, and that's because it actually basically is an interpolant function. So let's now put part 1 and part 2 together. So this theorem is due to Hrubesch and Pudlak. If I take any unsatisfiable CNF formula and I take any partition of the variables, then if there is a resolution, then if there is a resolution refutation of f of size s, then there's going to be a monotone circuit that computes this certificate function of size order s. Okay, and this is essentially, if you've seen feasible interpolation type statements, this is actually essentially a feasible interpolation type statement. So let's see a proof of that. And the proof is actually kind of one picture. So if we start with a resolution refutation of f, I'll give a size s rectangle DAG, which I defined earlier, just a DAG of rectangles in the Karshmer-Vigdorsen game. Well, okay, so here's my resolution refutation. So we have some input clauses, and we end up, all of these steps are the resolution rule, and we end up deducing the empty clause at the end of the day. Well, I'm going to partition. I have a variable partition, so I'll partition all of the clauses in the formula according to this partition. Maybe some of these parts are empty, but that's no big deal. And now, every single clause corresponds to a combinatorial rectangle. Like we just saw that a few slides ago. If I take any clause and I partition it, then I get a combinatorial rectangle that corresponds to it. So I can actually just write down the rectangles which correspond to each of these clauses. And we're actually done. This is a rectangle DAG that solves the monotone Karchmer-Wigderson game for the certificate function, because the certificate function, the monotone Karchmer-Wigderson game, is exactly this search problem. So just to confirm, so the root rectangle is 0 is everything. That's because the original thing was a proof of unsatisfiability. So everything is ruled out here. All the leaves are defining rectangles for this certificate, for the Karchmer-Wigderson game certificate function. That's because each input variable corresponds to a clause from the corresponding formula. And then finally, well, I mean, if I have some clause and it's deduced from two earlier clause by a resolution step, then if I just take a partition of the clauses, I mean, it's not hard to convince yourself that the rectangle for the output clause is contained in the union of the rectangles of the input clauses. In other words, if the clause is false, then if the output clause is false, then one of the two input clauses must have been false. So therefore, this satisfies all the properties of a rectangle DAG, and therefore by this earlier theorem, this is just equivalent to a monotone circuit computing the certificate function. Okay, cool. So now I've said this feasible interpolation a bunch of times. What exactly do I mean by that if you're not familiar with it? Well, it's in the standard form of feasible interpolation, you know, we have a sort of a partition formula with variables in one piece, and then we have to decide which side of the formula is satisfiable. Hrubesch and Pudlock actually showed that standard feasible interpolation can be deduced from this type of interpolation. So, and the converse direction holds as well. So in fact, like refuting the certificate function, computing the certificate function is essentially the same as doing feasible as a monotone feasible interpolant. And this was the key idea that enabled these lower bounds for cutting planes for random CNF formulas, just observing that feasible interpolation could be generalized to any formula with any variable partition. This is essentially what enabled us to prove lower bounds for random CNF formulas. And now once you have this basic idea, you can use it to deduce monotone feasible interpolation results for like lots of proof systems, almost trivially, as we just saw. So I spent a lot of time in this talk covering groundwork, but now once we have it, you can actually basically just replace the objects with rectangles, and you can prove feasible interpolation results essentially for free. So for example, we just saw resolution implies monotone circuits. This was, in this setting for the certificate function, this was proved by Hrubesch and Pudlock, but the prior result for this is, of course, due to Krychek. If you just make the rectangle DAG a tree and the resolution proof a tree, then we get the tree-like resolution implies a monotone formula. You just take the proof we just saw and just make it a tree, nothing changes. Hrubesch and Pudlock show that cutting planes can be used to give a real monotone circuit. This is a bit less trivial because what you don't get is a rectangle. This is somehow different in character from the other lifting results. In sort of my thesis work, we showed that null Stullinsats can be used to give a monotone span program. So in fact, you can use this idea that I just showed to give a feasible interpolation result very much in the style of this. The original result of feasible interpolation for span programs is due to Pudlock and Skal back in the 90s. But this gives a sort of a dead easy proof just by plugging in all of these, just by replacing every object in turn with a rectangle. In a paper we just submitted to ITCS, we showed that Shirali-Adams can be interpolated by what's called a weak monotone linear programming gate, or equivalently like this linear separation complexity. If you're not familiar with these models, you should just think of them as being like extended formulations of linear programs. And there was not prior to this a monotone feasible interpolation result for Shirali-Adams proofs. There was a feasible interpolation theorem due to Hakonyemi just from last year, but he gave a more classical result where actually you get an algorithm. So we actually just get a sort of a dead easy proof of feasible interpolation using these sorts of ideas. And kind of in a work that's kind of in preparation right now, you can apply the same idea that we did with Shirley-Adams to sums of squares to get an interpolation result, a monotone interpolation result for semi-definite extension complexity. Okay, so now lifting. So where does lifting come in all of this? Well, previously we just saw that a proof of F gives you a monotone circuit for the certificate of size S. Well, at the very start of the talk, I said something like this. I said lifting theorems are a converse to feasible interpolation. And that's because if we go back to this old theorem that I showed you, this is exactly what a lifting theorem is basically saying. It's showing that this monotone feasible interpolation theorem is in some sense tight, right? So here's the theorem I flashed much earlier in the talk. So if we start with an unsatisfiable CNF formula, then if we take this so-called index gadget, and then there's some monotone Boolean function, which we can now know, we can actually just take it to be the certificate function of the composed formula, such that the monotone formula size of this function is equal to the 2 to the resolution depth of this thing, right? And now 2 to the resolution depth, remember, is an upper bound on the formula size, right? So really what this is doing is it's proving a converse direction to feasible interpolation. It's saying proof size, this says proof size upper bounds give circuit size upper bounds. This says proof lower bounds give circuit lower bounds. Or equivalently, in the language we've been using in this talk, the rectangle tree size of this Karchmer-Wigderson game is the same as 2 to the resolution depth. Okay. And it's kind of helpful, I think, to sort of contrast this to the very basic example of lifting that we saw at the beginning of the talk, right? So here we start with something like what I'll call a degree measure, like the depth. And we end up getting something about a size measure. And the same thing occurs here. We start with a degree measure of this underlying thing, and we end up getting a lower bound on the size measure here. Okay, cool. So something that's kind of interesting and something that I'd like to explain in kind of this last part of the talk is this sort of relationship between the notion of kind of degree and size, right? So this these lifting theorems that I've seen that I've sort of written here, and the earlier example one we saw at the beginning of the talk with XOR, they don't seem to lift size to size, right? They always lift like depth to size, or like something different, something like that, or like width to size, or things like that, right? So in this last part of the talk, I'd like to try and explain a little bit where I think that comes from. But before I do that, let me kind of give you a bigger picture of the kind of lifting results that are known. So if we take, say, tree-like resolution size, well, we also have the corresponding degree measure is depth. And after doing this composition with an index gadget, well, then what we get is a lower bound on monotone formula size. If we start with a proof complexity degree of resolution width, then after composition with this index gadget, then we can actually get lower bounds on monotone circuit size. And then if we start with the proof system null-Stellensatz, it's an algebraic proof system that we haven't seen. Well, after doing this composition, we get monotone span program size and so on. So there's also lifting theorems that are known for, say, Shirley-Adams and for sums of squares, but they're actually incomplete. They don't go all the way in some technical sense. But I think that kind of the groundwork is there to sort of prove. So I think that this is actually a really interesting open problem to try to strengthen these lifting theorems here. Okay, cool. So I'm going to now move into the last part, which is on sort of a more general enveloping theory for all of this. I didn't time it very well, so I was planning on this part being the second part of the talk, which started 20 minutes ago. So I'm 20 minutes over time, so maybe I'll switch to the I was planning on switching to a handwritten slide now, so maybe I'll just do that.
So just to point out, the good thing with the second part is that, you know, people are free to leave at any point. So you should feel flexible. It's more like we're taking your time. You're not really taking ours because we drop out anytime we like. So, you know,
Okay, cool.
We're just excited to hear you share your insights.
All right, I won't feel bad then. Okay, so let me just create a. Let's just do a thing here. All right, great. Okay, so all right, so now in this last part of the talk, I want to talk about this this theory of TFNP. And total search problems. And if I can, allow me to sort of sting Mika's talk for everybody. So Mika's going to be talking in a few weeks on some joint work here in this very seminar. So if you're interested in this, if any of this sort of, if you find any of this interesting, then, you know, you can see Mika's talk for some of our recent joint work on this, in this kind of area. Okay, so we've seen that total search problems relate to. So total search problems are kind of the key thing that relate proofs to circuits. And now one of the main lessons of the past few years is that these relationships, they can be captured by using what subclasses of TFNP. So I'll just, it's kind of easier just to give an example. So let me give you, I'm going to define for you a class of search problems that I'm going to call PLS. This is a class of total search problems. And intuitively, PLS is going to consist of the class of search problems which correspond to finding a local optimum to some local search problem. So given a local search problem, find a local optimum. Okay. Or in kind of simpler language, given a DAG, just a directed acyclic graph, find a sync node. Okay, it's a very, very simple example of a local of a local search problem, right? If I started a node, I want to go to a node that is an outgoing, that is some successor of that node. Okay, and a local optimum will then correspond to a sync node. So you should think of PLS as being all the problems that I can reduce to solving this kind of problem. And now kind of the interesting thing is how we choose to do these reductions. Okay, so in this case for PLS, we'll use this following iteration problem. Okay, an iteration is defined as follows. So iter on, say, S. So iteration is going to have a set of, what we'll have is an ambient set of S vertices, 1 to S. Okay. And the input to the problem is going to be defined by a successor function on the set of vertices. So as input, oops, it should be S. We'll get some function that maps S to S. Okay. And think about this as whenever you take a point on this set of vertices, it's going to output a successor point. S is now a bad name. Let's call this successor. Okay, and now what is a solution going to be given this successor function as your input? Well, I want it to sort of correspond to a local. I want to think about this successor function as defining a DAG. Okay. So the solutions are going to be either violations to the DAG structure, or sync nodes if they exist. So I'm going to say a solution to this is going to be, well, the node 1 will be a solution if 1 is a local optimum. So think about 1 as like the starting point of our local search problem. We start at some point and then we want to go. So if 1 is a local solution, then if 1 is a local optimum, then we'll say that 1 is a solution. And then otherwise, I'll say that I is a solution if either the successor of I is behind I. So in other words, like it points to a node of lower potential. Or if there is some j less than I, such that the successor of j is I, and I is also equal to I. So you should think about it like we have some local optimum occurring at I. Okay. So this problem has, I'm going to call this problem iter or iteration, because you can think about it as kind of iterating the successor function over and over and over again until we find some local optimum or a violation of the DAG structure. But this also has some other names, which maybe if you've seen these sort of things before, you might have heard of. So one name is house sitting, the house sitting principle. And actually another name, which you might have also seen, even though it might not look like it at first, is pebbling formulas. This is actually a more abstracted version of a pebbling formula. So in a pebbling formula, you start at the root and then you walk your way down to, you can think of starting at the root and then walking your way down to a violated source node. Okay, so now what I want to do is I want to take this iteration problem and I want to use this iteration problem to solve search problems. In particular, the kind of search problems we've seen already in this talk. Okay, so let me just copy it down here. Okay, so let's let F be an unsat CNF. Then I'm going to say that search of F is in PLS decision tree. So a decision tree version of PLS. If there is an efficient decision tree reduction to iter. Okay. So what do I mean by that? Well, there should be some family of decision trees, which one for every single, which together the decision trees will define the successor function. And the decision trees should be defined so that whenever this iter problem has a solution, we should be able to extract a false clause of the underlying formula. So this is like a reduction between search problems. Okay. So more formally, for each I in S, I want to say there is a decision tree T sub I, which given it some assignment to the input variables is going to output J, which is going to be like the successor of I. Okay. So, and now efficient here is going to mean shallow. So you can think about it as being maybe polylog n depth. Okay, so
Robert, I have to confess something about, like, is it important for us to understand how pebbling formulas are a special case of this? I confess I had to think a bit to see that this was a total search problem, which I think I get now, but I'm not parsing the pebbling part.
Oh, it's not super important. I just wanted to say it in case you. It won't come up again. I just wanted to say it in case people had seen it before. Yeah, it is equivalent. The reason is that if you think about a pebbling formula, I mean, you can reword a pebbling formula as saying, like if I have a 0, then I have to go to the place where the 0 is in some sense, right? From the top down. And so actually it turns out that you can rephrase this iteration as one of these pebbling formulas more or less by like the only difference between iteration and pebbling formulas is that any single node can point to any later node. It's not restricted to just a node of a bounded output. It's not a totally local clause.
So should I think of 1 as the sink, and the first condition is kind of falsifying the sink, and if that's not the case, then I walk my way down through a falsified path or something?
Exactly right. Yeah, exactly right.
Okay, thanks.
Yeah, okay, cool. So yeah, maybe, sorry, I thought it was kind of clear that this would be a total search problem. Maybe I can just say out loud why that is. So every single node here has to point to a later node, right? So if either 1 points to itself, in which case it's a solution, and if that's not true, then 1 has to point to a later node, right? And then we have, well, for every single node, if the node points to an earlier guy, it's a solution, so it must point later. But if since there's only a finite number of nodes, there must eventually be a configuration like this, like a node, like a proper sink, a node pointing into a node and then a proper sink occurring at that node. So this is why this is a total problem. Okay, so let me get back to defining what I mean by a decision tree reduction here. So if there's an efficient decision tree reduction to iter, okay, so what I mean is that there's going to be a decision tree for every single successor point of this iter, which is going to output the successor. So for every input x, I'll get a successor function, which is kind of defined in a distributed way, like one for every single point. So like this decision tree for 1 is going to tell me where to point. And then I'll have a decision tree for 2, which will tell you where to point. And then so on. Okay. And then also, for each I in S, I'm going to have a label CI, or actually, let me call it like this, I sub C, which is a clause of the underlying formula. Okay. And then the idea behind the definition, behind the reduction, well, it's a reduction. So what we want is that any solution that gets output by the resulting formula, any solution that gets output by this resulting, after evaluating all these decision trees, should give me a solution to the original search problem. Okay. So if, say, O of X is the set of solutions in the iteration instance defined by the successor of X. So this is, remember, defined by this decision tree. Then for every single clause which occurs in this solution, I sub C is false. So in other words, all the solution of the all the iteration solutions will also be solutions to this underlying search problem.
And Robert, again, just to check that I'm following, I should think of X as the assignment that we're given to F, right?
Exactly. Yeah.
Okay. And then, of course, I could just have, I was thinking to myself then, well, let TI just query the assignment and just hard code it, like, output the falsified clause, which it could, of course, do, but then it wouldn't be efficient.
Then it wouldn't be
very deep.
Yeah. It could potentially be very deep. Exactly. Yeah.
So you want TI to somehow make some, like for a pebbling formula, you could make some local check and see if this is not like, the violated clause, then it's sort of TI has an idea of where to go next and which other clause to check.
Yeah, exactly. In fact, for a pebbling formula, there's a very simple example, is a nice example of a protocol. So if I have a pebbling formula, that looks like this.
Maybe we should say what pebbling.
I will say what it is. Yep. So what does the pebbling formula say? Well, it says think of all of these variables as being bits. And the pebbling formula say, okay, well, these input bits, the source nodes are all 1. The target node is 0. And then if I have xi and xj point to xk, then we have the clause that says, if xi and xj are true, then xk better be true. So in other words, all the sources are 1. If 2 nodes are 1, then the successor must be 1, and therefore we have a contradiction because the sink is 0. Okay. So you can use this to come up with a pretty simple PLS decision tree. Actually, you can use this structure, and the idea is pretty simple. So I'm going to have the PLS decision tree is going to have the exact same structure as the underlying graph. And it's kind of exactly what you just said, Jakob. So we're going to do some local checks at every single node. And then we'll use this to find a solution to the underlying problem. So initially, at the start node, what we'll do is we'll just query x1 and check if it's 0. And if it's false, and if it's false, if x1 is, say if x1 is 1, then what we'll do is we'll self loop here. So that way this becomes a solution. And that corresponds to this initial sync node being false. And then otherwise we'll point down here. This is if x1 is equal to 0. And now at each of these nodes, what are we going to do? Well, I'm just going to query what the value of this guy is and what the value of the 2 successors are. And if this node is 1, we'll self loop. So if x2 is, say, 1, then we'll do a self loop right here. And if otherwise, we'll point to here if x2 is 0 and x4 is 0. And we'll point to here if x2 is 0 and x5 is 0. So in other words, what we're doing is we're tracing the path of the 0 down the actual structure of the tree, right? So for every single node, we just query this value. We check if it's 0. And if it's 0, I'm going to find which one of the successors is 0, because one of them must be. If neither of them are 0, then I can create a sync node, because this one is now a false. This is now a false clause. Okay, cool. So now so now we have this definition of like a reduction to a PLS decision problem.
And then once you realize that xk was like, I guess, false, but xi and xj were both true, then you have the loop at k and you have a way of interpreting that then that particular clause was the falsified guy that we're going to answer for the search problem.
Right, exactly. If this was 0 and then these were both 1, then we can self loop again. And this will only happen, and then we will have a false edge here because, well, I mean, there will be at least one solution occurring somewhere because, this guy up here is going to be 0, and maybe this one was also going to be 0, right? So we have a false sync coming in right here.
Robert?
Yep.
Could you go back one slide, because I think I missed the definition of OX. Okay.
Oh, OX, yeah. It's the set of solutions that result in this successor function. So I look at this iteration principle, and then I just write down all the possible solutions.
Okay, thank you. Yeah.
No worries.
But like you're building it. So what I was a bit confused about that this successor instances is like comes from the particular assignment that we're looking at, but maybe that's
exactly.
like a natural. It's natural, I guess, when you start thinking about it. But
yeah, it comes from the assignment, because on different assignments to this graph, the violations are going to occur at different places, right? So you should think about
that kind of makes sense, yeah.
Yeah. Cool. Okay. So let me let me maybe kind of encapsulate a nice result here. If I have any CNF formula, then if there is a resolution refutation of F of, say, size S and width W, then there is a depth W plus 1 reduction of the search problem to the iteration problem on S nodes. So in particular, if there is a bounded width resolution refutation, then you can find a PLS decision tree that solves the search problem with, and the depth of the reduction is exactly the width up to plus or minus 1 is exactly the width of the underlying refutation. And so now how do we prove this? Well, in fact, we kind of already just proved it. You do the exact same thing as we just did. So maybe I'll copy this to another page. So what's the proof? Well, if I have a resolution refutation, so maybe I can draw one out here. So here's a simple example. Here's a resolution refutation. So how do I turn this into a PLS protocol or a PLS decision tree? Well, what I'm going to do is I'm going to take the idea of what I just did, right? At every single node of this refutation is going to become a node in the PLS tree. So I'll have like 1, 2, 3. And then at any single node, what you do is pretty simple. I'm just going to query all variables that occur in the clause. So look at this node, look at the corresponding clause in the refutation and query all the variables in it. If the clause is false, then we can query the clauses below it and point to the next clause that's false. If the clause is satisfied, then I'll make a self loop. So these sync nodes will always self loop. Yeah, so query all the variables in the clause. So if it's false, point to the new false clause. And otherwise self loop if there is no clause or if it's satisfied. And I mean, it's not kind of hard to convince yourself that what this is going to do is it's going to actually create a violation at one of these input clauses, because the root node is always going to be false. So if I'm given an assignment, I will point to one of these two false nodes right here. And then when I'm here, I'll query this node and I'll point to one of the two false incoming nodes. And then eventually I'll walk down the path and get to a false, some false sync node. So the proper syncs in this PLS tree are going to correspond exactly to the false clauses in the underlying resolution refutation.
Now, I guess people who've read their Atzeras Dalmau might start get curious whether there's some kind of converse, but it seems
there is indeed a converse, and I was actually going to prove it, but I'm kind of out of time. And now kind of a cool thing is that you can actually prove a converse relation. So if there is a PLS decision tree for search F, where each decision tree has depth D, then there's going to be a width order D size, say, S2 to the D resolution refutation. This direction is obviously a little bit harder, but it turns out that if you start with any PLS decision tree, you can actually extract from it a bona fide bounded width resolution refutation. So I'm running a little bit over time, so maybe I can just have one more slide just to sort of explain what I think is kind of the bigger picture here.
The super quick question. So the 2 to the D is like, because you don't really know what the decision tree is doing, so you might have to brute force sort of the resolution proof.
Exactly. Yeah,
but
yeah,
it's only over D variables. So like,
yeah, that's why D efficient means like polylog n or maybe even like log n depth. So if D was like constant width, then the result would be a constant width resolution refutation. Yeah, exactly. So you basically, every single decision tree just gets converted to a resolution proof in kind of the dumb way. You just brute force from the bottom up, but you don't know which one to evaluate, so you kind of have to do them all separately. So let me maybe give a big picture of the world. So actually not even constant width, you could even say order log n width. So I just showed you a result that said, okay, well, if you can solve the search problem in PLS, then this basically corresponds to bounded width resolution. But now there's lots of different total search problems that you could choose to look at. And this iteration is just a single example of them. So the original, so this whole idea of TFNP, although not with these decision trees generating the instances, rather with Turing machines generating the instances, was introduced by Papadimitriou kind of famously in the 90s, in the late 80s. And he introduced a number of nice subclasses of TFNP, which kind of correspond to different natural search problems. So let me write down, say, a few of them for you. So one that you might be familiar with is like this one. This is what the underlying search problem is, the pigeonhole principle. PPA is the search problem of basically finding, given an odd degree node in a graph, find another odd degree node. So it's encoding some sort of mod 2 counting principle. And then there's classes like directed PPA. So PPAD, this is sort of famous as being very closely related to game theory. And then there's PPADS, which is kind of related, which is another class that's related to this. Doesn't really matter what the definition is. So let me just, oops, that's not there. So let me just give you sort of a picture of things. And now with this description, you might start thinking that maybe these other classes might also correspond to proof systems. And indeed, it turns out that they do. So PPA turns out to correspond exactly to null-Stellensatz over GF2. This was proved in a paper with Mika a few years ago. This is our so-called adventures paper. And now PPAD, well, so up till now, well, okay, sorry, before I get to there, actually, let me say that FP corresponds to tree-like resolution, because FP is just solving your problem with a decision tree. And this is like the sort of classic result that a tree-like resolution and a decision tree are basically the same thing. So in the adventures paper, you know, we had answers for these three classes, right? These two are essentially folklore, and this was one of the new things that we introduced. But now in sort of an upcoming work, we have answers for some of these other classes. Maybe I can say that PPAD, this turns out to be, this was kind of already observed in the adventures paper, but this turns out to be low coefficient real Nullstellensatz. One direction of this was already observed in this paper, and then we had a converse direction. This turns out to be not so bad to prove. And then probably in what Mika's going to talk about in a few weeks is a new result which characterizes these PPADS. This turns out to be low coefficient Shirali atoms. This is in kind of an upcoming work. Okay. And now, so we get, the point of this is that we get lots of nice natural proof systems which correspond to solving search problems in these various TFNP subclasses. And now what you can do actually is you can just take this whole picture and imagine, instead of solving these things with decision trees, solving them instead with communication protocols. So instead of, now what I'm going to define for you, instead of having, just take the exact same definition that we saw a second ago, and instead of using a low depth decision tree reduction, use an efficient communication reduction to generate it. So if we go back to the definition of PLS, I mean, the definition is basically exactly the same. So now all I'll do is I'll replace each one of these decision trees here with some efficient communication protocol. And once you do that, you get communication versions of all of these classes, which solve total search problems. And it turns out that these things all capture circuit models. So this is going to correspond to monotone. TFNP is sort of corresponding to monotone Karshmar-Vigerson games, or games with small small rectangle covers. So PLS is going to correspond to monotone circuits. This is just a DAG, a rectangle DAG, like we saw much earlier in the talk. If we take PPA and the communication version, then what we end up getting is something called a span program over GF2. And then this is going to be monotone formulas. This is going to be real span programs, and etc. And now, once we have these two pictures sort of lined up next to each other, I think of lifting theorems as proving that if you can prove a lower bound in this picture, then you can prove a lower bound in this picture. And what we call monotone feasible interpolation is really saying, if I can prove a lower bound in this right picture, then you can prove a lower bound in this right picture. And so there's many very natural open problems that kind of suggest themselves from this. One of them is that I've only sketched out a fraction of the classes that you can define in TFNP here. And so proving and finding more proof systems and circuit classes that you can fit into this model is like a very interesting direction to take. One thing which I think is particularly interesting is to think about really a lot more powerful proof systems. Like, can we find classes that correspond to things like AC0 Frege or bounded depth Frege in this kind of model?
Do we even have, sorry, I mean, like, is cutting planes somewhere in this figure? Say?
Yeah, that's a great question. Cutting planes is not really in this model in a way that we fully understand yet. And that's because somehow cutting planes is of a bit of a different character. So remember, so there's this lifting theorem from resolution width to cutting plane size. And that kind of indicates to me, at least, that they're not quite, that you're not really going to find a nice characterization of it. It's because cutting planes has to do somehow with real communication protocols, not with Boolean communication protocols, and therefore the reductions here should be somehow different. That's another very interesting direction, is to try and figure out how that fits in. It's kind of interesting that cutting planes doesn't seem to fit in, even though we now know Shirali-Adams does. Yeah, so I guess, yeah. So one interesting problem is just to figure out more connections between these TFNP subclasses and circuits and proof classes. If you'd like more concrete problems, something that I'm really particularly interested in is in understanding what's going on with the pigeonhole principle. Like, is there a proof class or is there a circuit class that somehow corresponds to the pigeonhole principle in this picture? It's kind of not clear, because there's some results that say this class is less well behaved than we might expect, and so maybe there is no really natural thing. But one thing that you can say is that the communication complexity of this pigeonhole principle, it contains this sort of classic clique coloring problem, which was used to prove all these old monotone circuit lower bounds. So somehow the pigeonhole principle is saying something interesting, but I think one very interesting question is to try to understand what these proof models should be somehow. Yeah, okay, now I'm definitely running over time, so maybe I should pause before I just keep talking forever. Does anyone have any questions?
Robert?
Yeah.
So you are lifting with, like, you choose to use these decision tree reductions. Mm-hmm. And of course, I guess, I bet you thought about it. What if you use, don't know, low degree tests or whatever? I mean, some kind of notion which is more powerful than decision tree, but is not, of course, very powerful.
Yeah, that's an interesting question. And I think it's kind of related to this question about cutting planes. So in cutting planes, the sort of the classic feasible interpolation result for cutting planes interpolates cutting planes by monotone real circuits. And these correspond kind of to communication protocols where you have not standard Boolean communication, but with real communication instead. So this isn't a full answer to your question, but I think that somehow maybe there's something to be investigated here, which is what happens if instead of having Boolean protocols here, we have real communication protocols to define this class. Then I think you get things of a different character. Probably, maybe you can characterize cutting planes in a way like this. So for example, I can just say if I have PLS right here instead, and I put in a real communication protocol instead of like a depth one real communication protocol, you have to be a little bit careful here. But if I put in like a depth one real communication protocol here, then like there's a result of Rubesh and Pudlock basically says this is equal to a monotone real circuit. So I think that this is kind of I think it's a very interesting direction. Yeah.
Yeah, but I was thinking more on the other side, but of course, I mean, of course that would be related.
Yeah. On the other side, I mean, you could also imagine doing things like more algebraic type reductions, like you said, like low degree tests or like polynomial reductions. Yeah, it hasn't really been carefully explored. I'm not really sure how the characters of the classes would change. It kind of, I think it's kind of the same as changing the lowest possible class in some sense, right? Just like in complexity, if you change the strength of the reduction, it kind of changes the definitions of some of the classes above.
Thank you.
Would you view this also, Robert, as kind of starting to build a theory of reductions for proof complexity?
Yes.
I mean, it could be argued that in contrast to many other areas in computational complexity theory, in proof complexity, we sort of usually prove things with our bare hands, whereas many other areas have these elaborate systems of reductions. But here it seems like you're starting to build a rich web of...
Yes, and this is very explicitly that, in fact. Like using this kind of ways of expressing proof systems, you can now chain lower bound results and upper bound results together in very natural ways. Yeah, absolutely that, like definitely, definitely. Like this is I think decision tree reductions, at least for these weak classes, are kind of exactly the right notion of reductions between proof classes that we can use in many ways similar to like how reductions are used in standard complexity theory. Absolutely true. Yes. Yeah, I think that really thinking about these proof systems as search problems is a really somehow it's a very, very, very useful viewpoint because it brings algorithmic thinking to these kind of systems, which is very different from the way it's normally thought of, I think. There's also, of course, these classical TFNP results, which are very related. I think of these decision tree things like Krychek and Sam Buss, and there's some papers from the 90s sort of, and even later, sort of discussing different fragments of bounded arithmetic that correspond to these TFNP classes. And this is kind of the non-uniform analog of that theory, I think, is the way to interpret it.
Okay, thank you so much.
Albert,
Yeah.
so one question. Here you have some arrows in both models for inclusion, classes that are included in others. Are the arrows that are not present, are those known separations?
Good. Good question. So maybe I can focus on the proof side over here. Not all of the separations here are known. It's like one of the most famous separations that are left here actually is PLS versus PPP. Actually separate, like, so, okay, maybe take a step back for a second. So there's been a lot of work on proving oracle separations between these TFNP classes in classical complexity. And oracle separations turn out to follow from separations between these decision tree versions of the classes as well. Just like in classical complexity, many decision tree separations can be used, to prove oracle separations. So this is, in the decision tree world over here, kind of the biggest separation that's still open, I think, is PLS versus the pigeonhole principle. PLS versus PPADS is also open, but we might have an answer to that. Stay tuned, I guess. But over on the communication side, it's a lot less well as known. So most of these things are defined with like low coefficients. So I guess we know that like this separation is true, but like, yeah, this separations in both directions is still wide open here. Separations in both directions is still wide open here. So yeah. So yeah, it's quite a few of them are still open, I guess.
Okay, thanks.
There is a question in the chat from Bruno asking about the communication versions of PLS and TFNP. Can we say that the difference between PLS CC and TFNP CC is that PLS captures monotone Kochner-Wignerson games on total monotone Boolean functions, and TFNP does partial monotone Boolean functions?
No, not quite. TFNP is kind of like just any search problem with a small rectangle covering. All of these things are always defined with respect to just arbitrary total search problems. And this theorem that I showed earlier in the talk, argued that any total search problem with a small rectangle covering is equivalent to some partial monotone KW game. So you can think of PLS to the CC being like all of the possible total search problems that you can solve in here. And all of those will be equivalent to some partial monotone Karshmer-Wigderson game. That being said, also like the non-monotone Karshmer-Wigderson games are also in this class, right? Like the ones that correspond to standard circuit lower bounds. These also all exist in this class as well, but they're not like the complete problems for this class. They're like very, very, well, I mean, we'd love to be able to prove lower bounds for them, right? But they seem to be very hard to prove lower bounds for. So yeah, it's true that you, maybe to say a little bit more, it's true that there is this is a difference between the communication classes and the circuit model, because circuits necessarily compute total functions, right? Circuits will always compute a total function, like it'll always compute some total extension of a partial function. And some extensions could be hard and some extensions could be easy. So this is kind of you do lose something when you go to communication, and that's this kind of, well, maybe I should say you should lose something when you go to circuits. And that's this kind of differentiation between partial and total. So this model really shows the difference between partial and total. It's kind of the way to say it, I guess.
Another notable, omission from the picture for those of us who love weak proof systems is, I guess, polynomial calculus. Where is it?
No idea. It's a great question. Yeah, I don't know. It should be somewhere. It should be somewhere up here. But yeah, it should obviously contain null-Stalin sets. Also, sum of squares should be in here somewhere. But also, we know sum of squares can refute the pigeonhole principle, so it should also be up here somewhere.
So do you think there are new TFNP classes that would be there? I remember Christos at one point was thinking about the Ramsey class.
Yep. Yeah, I don't remember. Ramsey, I think, is actually contained in the pigeonhole principle class. I mean, there's lots of classes that I haven't defined here, but yeah, I do think that there probably are natural classes that correspond to these things. Polynomial calculus is a great example. There should definitely be a natural TFNP class that I think should correspond to polynomial calculus. And because of the simulation of polynomial calculus with bounded width by bounded width resolution, I think that it should probably contain both PLS and PPA, because it should be able to simulate both null-Stalin sets and simulate resolution. So it should be somewhere up here, but I don't really know exactly where.
Mm-hmm.
It's interesting that you get Shirley-Adams with low coefficients in the picture, right? So maybe polynomial calculus, you would also get something with low coefficient, or is this particular to Shirley-Adams?
Well, this is because it's over the reals and we need to discretize. So there is a way actually to get a high coefficient one that kind of lives up here somewhere, using kind of the same techniques and encoding the numbers in binary. With polynomial calculus, this, depending on the field you choose, it's not really a problem, right? Like over F2, I don't really have to worry about coefficient size. It's always going to be a constant relative to the input. That's why this is just straight up null-Stalin sets degree. And that's why this is like low coefficient real null-Stalin sets.
Okay. And is there any chance that PPP would be sum of squares, or you said that it doesn't behave well, so it probably won't?
I think it doesn't behave well, so it probably won't. I think it's probably bigger. Even, yeah, there should be some sort of low coefficient sum of squares class that should simulate PPP, I think.
But do we know anything besides pigeonhole principle that sum of squares can do? That cannot be.
Well, I guess there's tons of these approximation problems, but yeah, for CNF formulas, it's a good question. Yeah, for CNF formulas, I don't know, actually. Yeah, I can't think of anything that would be doable in PPP anyway. Yeah, it's a good question.
Okay, so thank you again, Robert. I'm starting to think that we should maybe wrap this up. This has been a wonderful survey talk, and also opening up some fascinating new perspectives, and certainly lots of room for further contributions, it seems. So thank you so very much for a wonderful talk, and I'm applauding on behalf of everybody. Thank you so much.
Yeah, thank you again for having me. I was happy to do it.